Alright, finally I am going to have a video with an appropriate background and no cats in the way. Alright, so now we've learned how to do partial pressure calculations, and we're going to just kind of extend that into collecting gases over water. It's the same sort of thing. It's the same type of math, and I think the same type of reasoning. I don't know why they put it in two separate sections. Okay, when we collect gases in the lab, what we are going to do is bubble the gas up through basically a container of water and collect it in this gas collection tube called a eudiometer tube. So it's common to synthesize gases and collect them by displacing a volume of water. So as more and more gas bubbles rise up the gas collection tube, the more water gets pushed out the bottom. So in order to figure out the amount of gas produced, we first have to know the pressure of our gas. And just like our Dalton's law of partial pressure, the total pressure is equal to the pressure of all the parts. So when we collect a gas over water in the lab, we're going to have a gas pressure and a water pressure because water evaporates. If we used mercury, this wouldn't be as much of a problem, but we'd have other issues to deal with. Sorry. So P total equals the pressure of the gas plus the pressure of the water. So when you do a problem like this, it's going to give you the P total. Okay? And then it's going to tell you to go look up the pressure of water in Appendix B in the back of the book, and you just subtract it off. The total pressure. So the vapor pressure of water, though, is not a constant. It depends on temperature. The higher the temperature, the more the water evaporates, and the higher the water vapor pressure. So in Appendix B in the back of your text, you can find the different vapor pressures of water at different temperatures. Or you can be lazy like I am and just Google it real quick on your phone. Okay, so this is the kind of thing I mean. Okay, here they have I don't know, it's purple, so I'm wanting to say it's like potassium permanganate or something, but they are decomposing this solid substance with heat, and it's producing some kind of gas. And the gas is traveling down the tube and then up into this gas collection tube. Okay, we're going to have ones that are about half a meter long. They're 50 milliliters capacity, and as more and more gas comes out of this tube and rises up to the top, it's going to push the water out. Okay. Now when we go to measure the volume of our gas and really the pressure of our gas in the collection tube, we're going to move the tube around, up and down into the water, kind of changing the pressure a little bit on our gas until the level of water inside the tube is equal with the level of water outside the tube. At that point, remember the manometers with the height differences between the mercury levels and such? Same principle. When the two levels are the same, the pressures are equal. So when the level of water in our gas tube is equal to the level of water in our big puddle of water outside of it, then we know that the pressure inside the tube is equal to the pressure outside the tube. And when we do a lab, I'll have my digital barometer ready that tells us the pressure of the room. And then once we get our gas to that same pressure, once we get our gas to that same pressure, we'll simply read the volume here on the eudiometer tube, and it'll tell us how many milliliters of gas we made. So the total pressure, though, here is due to the gas being collected, the oxygen, let's say, and the water evaporating, the water vapor. So in this example, it's methane gas being produced and collected over water. So this volume of gas right here, like let's say it's 10 milliliters, not all 10 of it's methane. Some of it is water vapor. So we have to, I said volume, didn't I? I meant to say pressure, I'm sorry. So let's say this is 5 ATMs of pressure right here. Not all that pressure is coming from methane. Okay, some of it is coming from the water vapor. So we just simply need to correct that by subtracting off the water vapor. So we just need to see a problem like that. I believe this is the one that we have worked out in the sample problem video. It gives us the volume, temperature, and pressure of our gas and asks for moles. Well, that pressure is not really of the oxygen. That's the oxygen and the water. Okay, so if we look up water's vapor pressure at this temperature, at, what was it in Celsius, 26 degrees Celsius, we see in Appendix B that the water pressure is 25 torr. The total pressure of both gases, the oxygen and the water vapor, is 765. So subtract the 25 off of 765, and I get that my oxygen pressure is just 740. And then I put it in ATM because we're getting ready to do a perv-nert problem, and so it needs to be an ATM. How many moles of oxygen were collected? Okay, all we had to do was figure out the precise, exact, correct pressure, and then do perv-nert to solve for moles. So that's how many moles of oxygen there are. How many grams of KClO3 were decomposed? Well, make sure you realize this answer here is moles of oxygen, not moles of KClO3. I've already seen people struggling with that already with the bookwork. Pay attention to what chemical it is, okay? You can only do perv-nert for a gaseous substance. All right, so now for part B, okay, I have to take my moles of oxygen and stoich it to moles of potassium chlorate. There's 3:2 ratio, and then convert it to grams of KClO3. So that was it for collection over water. It's basically just an extension of partial pressure problems. All right, now for the fun part, the theory behind all these laws. I always struggle with the decision of whether or not to start with this or finish with this. The book puts it at the end, but a lot of this stuff we've kind of addressed already. This is just simply the theory that explains why the laws are true. Okay, laws summarize facts. P times V is equal to nRT, pressure times volume, initial is equal to the final pressure times volume. These are all laws, mathematical equations. Why do they work? Well, that's what the kinetic molecular theory states. Kinetic, if you remember, means motion. So this theory is all about the motion of the molecules, explaining why gases behave the way they do. All right, so it's a theory of moving molecules. Remember the difference between a law and a theory. A law states, a theory explains. Okay, so we already, picture gas molecules like this. There's even more empty space in between them than this. They're flying around real fast. They're not interacting with each other for the most part. So the basic premises that we have to understand here to understand the behavior of gases are this. Gases consist of a large number of molecules in constant random motion. There's a whole bunch of gas particles flying around really fast, bouncing off the walls, and then the combined volume of all the molecules is negligible compared with the volume of the container. Negligible means so small it doesn't matter. So when you're looking at like a 1 liter balloon full of air, if you could just look at the atoms in the air and ignore all the empty space, it would be minuscule. It would be negligible. Okay, there's the gas molecules themselves take up very little space. So when we talk about the volume of gases, all that space is mainly empty space. All right, the other part of the kinetic molecular theory, which I'm just going to say KMT for now on for the theory, KMT. The other part of the KMT is that it's kind of an assumption that we make that the intermolecular forces, the forces between the gas molecules, are negligible. So we assume that 21% oxygen that is flying around in the air is ignoring all the other gases and even each other. So we assume the oxygen molecules that are flying around never slow down as they pass each other. They're never attracted to each other because there's so much space between them and they're moving so fast. Now, we also have to realize that energy can be transferred between molecules during collisions. But, just like if you run into a wall, there's some energy transfer there. But the average kinetic energy is constant at constant temperature. What does that mean? Well, when I'm looking at a balloon full of air at room temperature, some of the gas molecules are moving faster than others. Some are moving slower. Okay? But the average kinetic energy, if we average it all out, that's going to stay constant as long as the temperature is constant. Some are above average, some are below average, but the overall average is going to stay steady. Now, if we heat up the gas molecules and raise the temperature, well, then the average kinetic energy would increase. And then we also assume that the collisions are perfectly elastic, meaning that no energy is lost due to friction or anything else when the gas molecules collide with the walls of the container. So when the gas molecules bounce off the walls of the inside of the balloon, we're assuming that they do not slow down. It's a perfectly elastic collision. And in reality, in the physical world, there is no such thing as a perfectly elastic collision. If you run into a wall, jump on a trampoline, whatever, there's always some energy of motion that gets kind of wasted as other energies. It's lost as friction, sound, you name it. All right, the average kinetic energy of the gas molecules is proportional to the absolute temperature. I think that's exactly what this says right here, so I'm sorry that's a little redundant. I guess the thing to make sure, once again, because we're talking about gases, their energy is proportional to their absolute temperature. So their absolute temperature means in Kelvin. This has to be in Kelvin in order for it to work. All right, so the kinetic molecular theory gives us an understanding of pressure and temperature on a molecular level. Okay. Pressure of the gas is caused by the collisions with the walls of the container. Just remember that. You need to be able to visualize these gases flying around in your mind. So the pressure results from the collisions with the walls of the container. How high the pressure is, the magnitude of the pressure, is determined by how often and how hard the molecules strike the walls of the container. Okay. The temperature in Kelvin, the absolute temperature, is the measure of kinetic energy, and it's that temperature that determines how hard the molecules strike the walls of the container. Okay. As temperature increases, the average kinetic energy of the molecules increases. Okay. Which that means kinetic energy is due to the mass of the particles and their velocity. So the faster the gas molecules are going, the more kinetic energy they have. Okay, so how does this all apply to gas laws? Well, the effect of an increase in volume, assuming temperature is kept constant, is as follows. Okay, as volume increases, the kinetic energy of the gas remains constant because the temperature is constant. The molecules aren't going to be flying around any faster or slower, but because the container is bigger, okay, there's going to be fewer that actually hit the walls of the container. Right? So temperature stays constant. They're all flying around at the same speed, but because the container is bigger, they're not going to collide as frequently. So that means the pressure will drop. So this is how you use the kinetic molecular theory to explain Boyle's law. Why is it that as volume goes up, pressure goes down? We need to be able to explain that in terms of the kinetic energy, in terms of the motion of the molecules, in terms of the temperature. So it's just basically putting everything together that we've been learning. Now, if we increase the temperature at constant volume, okay, so temperature's increasing, molecules are moving faster, but the volume of the container isn't a balloon or one of those cylinders with the movable piston. It's a constant volume. It's a container that cannot change size. What happens if we increase the temperature then? Well, the average kinetic energy is going to increase. They're going to have more energy. They're hotter, so they're going to be flying around faster. And therefore, there's going to be more collisions with the walls of the container. And that change in momentum in each collision, each molecule is going to then strike harder. And that's going to make pressure increase. There's more collisions and harder collisions, so pressure will go up. So if temperature goes up, pressure goes up. We've already called that one the Gay-Lussac law. All right. That's one we did in the sample problem, so I will stop here. We're not done yet, though.